Okay, so at the end of the last video, we were talking about nuclear fission, the splitting together of a larger atom, a larger nucleus, into two smaller ones, but two that are nearly equal in size. I just rewrote it down here because I realized I was probably going to run out of paper up there, and I had to do something while I was waiting for the last video to upload. Okay, so the two most common elements that we use for fission are uranium-235 and plutonium-239. We shoot a neutron into uranium-235, it absorbs it, and for an instant it's like 236, but then it splits. So one of the possibilities that could happen is that it could split into Xeon-140 and strontium 94, XR 94, it's 38, right? And then there are two neutrons left over, plus Q, which is energy. Okay, and so at the end of the last video, I was saying in the uranium-235, there's a lot of binding energy needed to hold that many atoms, that many nucleons inside the nucleus of that atom. But when it splits into two smaller ones, the energy per nucleon goes down, not as much as needed, and so what isn't needed anymore is given off as energy. Okay? And there's a couple of excess neutrons too. Another possible reaction for 235. So we start the same, we still send in a neutron. And another possible reaction is, so it goes to 236 again, would be barium, and it's 141, and barium is 56, and krypton 92. And krypton is, I cannot see, I need my glasses checked, my eyes checked, something, 36, krypton is 36. And again, you'll see there's excess neutrons left over, which are given off, and then, of course, plus energy. Now, so the neutrons being given off are going to play a role because you have to add a neutron in, and then there are neutrons given off. So when we do this process in a controlled manner, we're going to take these neutrons that are given off, and we're going to feed them back in. We're going to use them to split more uranium-235s, right? And so then it becomes a cycle. When either of these two reactions are controlled, then we can harness the energy, and this is what we do in a nuclear reactor. Okay? If it's an uncontrolled reaction, then and it continues to feed itself, then it can go critical. It can go big and bad very quickly. And that's what happens in an atomic bomb. Okay? Now, so knowing that these are, and there's probably others, I'm just possibilities for the uranium-235. But it's uranium-235 that's going to split. We've seen uranium-238, we've seen other isotopes of uranium, but the one that is fissionable, the one that we're able to split is 235. Now the sad part is 99.3% of all the uranium that's mined is uranium-238, not 235. Okay? And uranium-238 is not fissionable. Of the other 0.7% of the uranium that is mined, most of it is uranium-235. The thing is, as we mine it, we can't separate out the 235 and the 237. So every truckload of uranium we get, every kilogram of uranium we get, only 0.7% of that is useful uranium for us, useful in the sense of using it for nuclear power. Now we take this uranium-235, 238 mixed together, and we can actually enrich this. So we are able to enrich it a bit, and we can get the percentage of uranium-235 up to 3%. Which is better than 0.7%, but it's still pretty tiny. And so once we have enriched it, and you might say, how come you can't do more? It's just too expensive, too time consuming. In the end, it's not worth it. So we take the uranium-235, 238 that we mine, and we pack it into these little pellets. And they're almost like, you can almost think of the pellets as if they're, pellets that you would put in a gun or something. So we pack them into these little pellets. And remember, only 3% of them are useful. And then we put them in these big, long fuel rods, which we're then going to put in a nuclear reactor. Okay, so the pellets are all packed in here. And then we put these fuel rods in the nuclear reactor, and we use them as fuel for the reactor. When a fuel rod is all used up, it means that we've split all the uranium-235, but there's still going to be 97% of the fuel rod is still going to be uranium-238, which is radioactive and dangerous. So that's why we always talk about the issue of what are you going to do with your nuclear waste from these nuclear reactors. So we've used up all the 235 in this rod, which is really only 3% of the whole thing, and then we have to figure out what are we going to do with this rod. And if you remember when we were doing half-lives, the half-life of uranium-238 is huge. Like, we're talking like millions of years. We're not talking like, 2 weeks or even 10 years. And so it's one of the reasons why the nuclear industry is controversial, because we're creating this nuclear waste, which is hazardous. Like, where are we going to put them to store them safely? And when we're only using 3%, it's like, is it worth it? Well, on the is it worth it question, one little pellet of uranium, 3% of which we can use, releases 200 times more energy than a ton of coal. One little pellet, 200 times more energy than a ton of coal. So for the people who are supporters of the nuclear energy industry, they would say that's what makes it worth it. Look at how much energy we can get out of this tiny little pellet, whereas someone else has to burn a ton of coal, which also isn't good for the environment. They have to mine it, and then they have to burn it. So that's where that's part of where the controversy comes in. Okay, I'm going to do one last piece, and we'll leave how the reactor actually works for the next day. But the one last piece is, I had said a few minutes ago that the ideal is that you take these neutrons that are given off, and you feed them back into the reaction. So one uranium, when it's split, gives you off 2 or 3 neutrons, depending on which reaction it is. And then if you can take those and split 2 or 3 more uraniums and get 2 or 3 more off, and it goes pretty quickly. It can become what's called a chain reaction. Okay, a chain reaction. And a chain reaction means it's self-sustaining. Self-sustaining. Right? That once you start it, it can go on its own. Now, for that to be true, you need a critical mass of uranium. And you also need to be able to feed back in the neutrons. If it's a controlled reaction, this chain reaction is controlled, then we can get the energy out of it. If it's not controlled, then it would be like in an atomic bomb. It is really important to control it, because a chain reaction which begins with 1 atom of uranium-235 can produce 2 times 10 to the 13th joules of energy in 1 microsecond, in 1 times 10 to the negative 6 seconds. So another reason why the nuclear industry is controversial is this can get out of control quickly. If it's going to create 2 times 10 to the 13th joules of energy in a microsecond, you got to be really careful with it. Stay tuned.